I would say that orthogonality is the key to understand Fourier series expansion. In engineering and science, we deal with waveforms. A waveform may represent a characteristic of a phenomenon with respect to a certain variable, or variation of a quantity with the evolution of a certain variable, for instance time. In order to apply a mathematical method to a given waveform, the waveform must be represented by a simple mathematical expression. If a given waveform is represented by a complicated equation or just by numerical data, then applying a certain mathematical method would be quite complicated. For representing a given waveform by a simple mathematical expression, note that there are basically three different categories. If you are interested in local behavior of a waveform, use Taylor series. If a given waveform is periodic and you want to capture the entire behavior of the waveform, then use Fourier series. If a given waveform is single-shot and you want to capture the entire behavior of the waveform, then use Fourier or Laplace transform. So, when you want to capture the entire behavior of a periodic waveform, you should use Fourier series. Fourier series expansion tries to approximate a periodic waveform by a sum of sinusoidal waves. Each sinusoidal wave must have a period whose multiple is the period of the given waveform. In other words, the frequency of each sinusoidal wave must be an exact multiple of the frequency of the given waveform's period. I presume that you are familiar with describing a sinusoidal wave by an exponential function with an imaginary argument. If not, watch the video or read a text entitled Oscillation Kernel. Since Fourier series is often applied to time-periodic waveforms, let's consider a time-periodic function f of t where t is time. When the period of f of t is large T, then its frequency is f equals 1 over large T and angular frequency is omega equals 2 pi over large T. Fourier series expansion approximates f of t by a sum of sinusoidal waves. F of t is equal to the sum of Cn multiplied by e to the in omega t as n goes from negative infinity to infinity, where Cn for negative, 0 and positive integers are called Fourier series coefficients. Note that the angular frequency of each sinusoidal wave e to the in omega t is an omega, which is an exact multiple of the given waveform's angular frequency omega. Why are they exact multiples? It can be clearly explained by the following counterexample. What if a sinusoidal wave whose frequency is not exactly a multiple of the given waveform's frequency is included in the series? Then, that component, included in the summation, will collapse the periodicity of the given waveform. So, each sinusoidal component must have a frequency which is an exact multiple of the given waveform's frequency. Fourier series expansion says that a periodic waveform can be approximated by a sum of sinusoidal waves having frequencies which are exact multiples of the frequency of the given periodic waveform. Those sinusoidal waves are often called harmonics. From now on, We call the complex sinusoidal wave e to the I omega t as an oscillation kernel in this video. Before talking about the main topic of this video, which is orthogonality, let's check the following two interesting points. The Fourier series expansion formula adds up not only for positive frequencies but also for negative frequencies, because the summation starts from negative infinity. What is a negative frequency? In our real world, causality is always satisfied. Causality means that a physical or engineering system does not give an output for an input before the input is received. Under this situation, an oscillation kernel with its coefficient, Cn multiplied by e to the in omega t, which exists as a part of a waveform in this real world, is always accompanied by its complex conjugate counterpart. The complex conjugate of Cn multiplied by e to the in omega t is equal to the complex conjugate of Cn multiplied by e to the negative in omega t. Look at this equation. The accompanied complex conjugate wave is actually its negative frequency component. If these two components are superimposed, then applying Euler's formula gives Cn multiplied by e to the in omega t plus the complex conjugate of Cn multiplied by e to the negative in omega t is equal to Cn multiplied by cosine in omega t plus I sine omega t plus the complex conjugate of Cn multiplied by cosine n omega t minus I sine omega t is equal to twice the real part of Cn multiplied by cosine n omega t minus twice the imaginary part of Cn multiplied by sine n omega t, which is equal to twice the magnitude of Cn multiplied by sine n omega t plus theta n, where theta n is equal to negative argument of Cn. Amazingly, the result is not a complex number but a real number. Causality, which is always satisfied in this real world, forces the complex conjugate constraint mentioned above, thus always cancelling out the imaginary part and leading to the fact that waveforms observed in this real world are all real. The zeroth order coefficient C0 is an exception. It is always real and does not have a complex conjugate counterpart. For electrical engineers, it is a DC, direct current component. If you are further interested in this topic, watch the videos or the texts entitled Oscillation Kernel and Understanding Euler's Formula through its Derivation. Another point to note at this point is the fact that the Fourier series coefficients are complex valued except the zeroth order coefficient. If a coefficient Cn where n is non-zero is written as the polar form, Cn is equal to Rn multiplied by e to the I theta n, then the nth order oscillation kernel with its coefficient can be written as Cn multiplied by e to the I n omega t is equal to Rn times e to the I theta n times e to the I n omega t is equal to Rn multiplied by e to the I n omega t plus theta n. So, the coefficient Cn specifies not only the amplitude Rn of the oscillation kernel but also the phase angle theta n. The use of a complex-valued coefficient Cn makes it possible to specify both the amplitude and the phase angle by a single number. Okay, let's talk about the main topic, orthogonality. If we are talking about vectors, orthogonality can be interpreted as perpendicularity. If the angle formed by two vectors is 90 degrees, they are orthogonal. In other words, if the inner product of two vectors are 0, they are orthogonal. This concept can also be applied to two periodic functions. Let's define the inner product of two periodic functions p of t and q of t. P of t is multiplied by the complex conjugate of q of t, and the product is integrated for a common multiple of the period of p of t and that of q of t. The inner product of p of t and q of t is equal to 1 over large T multiplied by the integral of p of t multiplied by the complex conjugate of q of t from negative large T over 2 to large T over 2, where large T is the common multiple of the periods mentioned above. In Fourier series, we use oscillation kernels e to the in omega t for the expansion. So, let's calculate the inner product of p of t is equal to e to the im omega t and q of t is equal to e to the in omega t. The inner product of e to the im omega t and e to the in omega t is equal to 1 over large T multiplied by the integral of e to the im omega t multiplied by e to the negative in omega t from negative large T over 2 to large T over 2, is equal to 1 over large T multiplied by the integral of e to the im minus in omega t from negative large T over 2 to large T over 2. The period of e to the im omega t is Tp equals 1 over mf equals 2 pi over m omega, and that of e to the in omega t is Tq equals 1 over nf equals 2 pi over n omega. So, we can use T equals 1 over f equals 2 pi over omega as a common multiple. In the case of m equals n, the integrand becomes 1. Thus, the inner product is 1 over large T multiplied by large T, which is unity. This implies that e to the im omega t and e to the in omega t are in the same direction and thus not orthogonal to each other, of course because they are the same functions. In the case of m is not equal to n, on the other hand, the integrand is e to the ik omega t where k equals m minus n is a non-zero integer. Since large T is a multiple of the period of e to the ik omega t, integrating e to the ik omega t for the period large T is 0. Thus, the inner product is 0. In other words, e to the im omega t and e to the in omega t are perpendicular to and thus orthogonal to each other. Oscillation kernels for different orders are orthogonal to each other, and they form a set of orthogonal bases. Let's look at the Fourier series expansion formula again. F of t is equal to the sum of Cn multiplied by e to the in omega t, as n goes from negative infinity to infinity. Fourier series expansion represents a given periodic waveform by the sum of the orthogonal bases, e to the in omega t, for negative, 0, and positive integers. Especially when we use large and positive frequencies, their negative counterparts on the zeroth order term only to approximate a given periodic waveform, f of t, we may use f of t is nearly equal to the sum of Cn multiplied by e to the in omega t, as n goes from negative large N to large N. This Fourier expansion tries to approximate f of t by the sum of two large n plus 1 orthogonal bases. What is the inner product of two vectors? It is a projection of one vector to the other. So, what does this mean for two functions? The inner product of f of t and e to the in omega t is equal to 1 over large T multiplied by the integral of f of t multiplied by e to the negative in omega t from negative large T over 2 to large T over 2. This is the projection of a periodic waveform f of t to the basis e to the in omega t. Well, this means that we are calculating how much e to the in omega t component is included in f of t. This is actually the Fourier series coefficient Cn. So, we may be able to calculate Cn by Cn is equal to 1 over large T multiplied by the integral of f of t multiplied by e to the negative in omega t from negative large T over 2 to large T over 2. Let's call this an extraction equation in this video. But, is this equation true? Okay. Let's assume that a given periodic waveform f of t consists of the nth order component with its coefficient, a, multiplied by e to the in omega t, and the remaining part g of t. F of t is equal to a multiplied by e to the in omega t plus g of t. Substituting this into the extraction equation to get Cn gives Cn is equal to 1 over large T multiplied by the integral of a multiplied by e to the in omega t plus g of t multiplied by e to the negative in omega t from negative large T over 2 to large T over 2 is equal to a over large T multiplied by the integral of e to the in omega t multiplied by e to the negative in omega t from negative large T over 2 to large T over 2 plus 1 over large T multiplied by the integral of g of t multiplied by e to the negative in omega t from negative large T over 2 to large T over 2. According to orthogonality, the first term is a. The second term is 0, since g of t does not include e to the in omega t component. So, Cn is equal to a. We are able to extract a from a given waveform using the extraction equation. So, Fourier series expansion gives us a way to represent a given periodic waveform, f of t, by a sum of oscillation kernels. F of t is equal to the sum of Cn multiplied by e to the in omega t, as n goes from negative infinity to infinity. Although it looks complex valued, the imaginary parts are cancelled out due to causality. So, it is real valued. You can calculate the values of the coefficients Cn, which are the magnitudes of the oscillation kernels including their phase angle information, using Cn is equal to 1 over large T multiplied by the integral of f of t multiplied by e to the negative in omega t from negative large T over 2 to large T over 2. In practical applications, we use only up to the large nth term. Large n positive frequencies, their negative counterparts and the zeroth order term, altogether 2 large n plus 1 terms. In other words, Fourier series expansion gives us a way to decompose a periodic function into weighted oscillation kernels, and the weightings, which are complex valued so as to include phase angle information, are the Fourier coefficients and can be obtained as the inner product with respect to oscillation kernels. The oscillation kernels form a set of orthogonal bases. So, the inner product of different order oscillation kernels are 0. Calculating a Fourier coefficient is equivalent to calculating the projection of the given periodic waveform to that oscillation kernel using the inner product formula, or the extraction equation in this video, thus extracting that oscillation kernel's weighting. The resultant Fourier coefficient is the weighting of the oscillation kernel. When we use up to the large nth term, we are representing a given periodic waveform by the sum of 2 large n plus 1 weighted oscillation kernels. Since the 2 large n plus 1 oscillation kernels form a set of orthogonal bases, they are like unit vectors in a 2 large n plus 1 dimensional space. And their weightings, in other words, Fourier coefficients, are the lengths of those unit vectors. So, Fourier series expansion can be viewed as a way to represent a periodic waveform by a sum of weighted vectors in different or independent directions. Finally, let's apply Fourier series expansion to a periodic square waveform. This figure shows a periodic square waveform whose period is large t. So, its angular frequency is omega is equal to 2 pi f is equal to 2 pi over large T. The Fourier coefficients of this waveform are calculated by the extraction equation. Cn is equal to 1 over large T multiplied by the integral of f of t multiplied by e to the negative in omega t from negative large T over 2 to large T over 2. Then it is divided into the part from negative large T over 2 to 0 where f of t is 0 and the part from 0 to large T over 2 where f of t is 1. Then, it is equal to 1 over large T multiplied by the integral of e to the negative in omega t from 0 to large T over 2 is equal to minus 1 over in omega large T multiplied by e to the negative in omega t from 0 to large T over 2. Here, let's suspend this calculation and simplify omega large T. Omega large T is equal to 2 pi over large T multiplied by large T, which is 2 pi. Okay, let's resume the calculation of Cn. Cn is equal to minus 1 over I 2 pi n multiplied by e to the negative in pi minus 1, which is equal to I over 2 pi n multiplied by negative 1 to the nth power minus 1. The equation above is not applicable to n equals 0, since there is n in the denominator. To get C0, we calculate from scratch. C0 is equal to 1 over large T multiplied by the integral of f of t multiplied by e to the 0 from large T over 2 to large T over 2, which is divided into the part from negative large T over 2 to 0 where f of t is 0 and the part from 0 to large T over 2 where f of t is 1, then it is equal to 1 over large T multiplied by the integral of unity from 0 to large T over 2, which is 1 over 2. So, we get the Fourier coefficients of the periodic square wave. Cn is equal to 1 over 2, when n equals 0, Cn is equal to minus I over pi, n, when n is an odd number, and Cn is equal to 0, when n is an even number. It is interesting to superimpose f of t is nearly equal to the sum of Cn multiplied by e to the in omega t as n goes from a negative large N to large N, on the given waveform. When large N equals 0, so only with the constant term, we get this. When large N equals 1, which means we include n equals 0 and n equals plus minus 1 only, we get this result. When large N equals 3, when large N equals 5, if we include up to the 19th order, then we get this result. As we increase the number of terms included, the Fourier series expansion better approximates the given waveform. I hope you have reached real understanding of Fourier series expansion. Thank you.